of rocks in the solid earth. And then geomorphology, that means the shape of the earth's surface in terms of elevation and its derivatives. And geological structures or tectonics in the earth crust. Okay. See, a variety of physical, chemical, and tectonic processes are basically responsible for molding this shape of the earth surface, the composition of the earth, and the structure of the earth. And if you see the illustration on the right side, you see that the earth has essentially a layered structure. We know that. And it is made up of 3 layers, major layers. Okay. The upper one is the crust, then comes the mantle, and the lower one is the core. There are subdivisions like upper crust, lower crust, okay, upper mantle, lower mantle, upper core, lower core. I'm not going to that details. Now you see the outermost part of this earth is called a lithosphere. And this lithosphere, it is essentially consists of the entire crust and a small portion of the upper mantle. And below that, there is the asthenosphere. Now they see this lithosphere, it is not continuous over the earth. Okay, it is divided into pieces, and some pieces are very large. There is the major pieces, and many are small pieces. And these pieces are known as the tectonic plates. Now see these plates, okay, they are floating over the asthenosphere. That is a viscous material. Okay. Now these plates, they interact with one another, and basically it is governed by this convectional force that is coming from inside the earth. Okay. And when these plates are moving and they are interacting with each other, okay, so this plate tectonics theory that explains this restlessness of the earth due to the movement of the plates in different directions and in different speed. Okay. Now coming to your topic today, that is the remote sensing applications for geological studies. So first we need to understand what is remote sensing, and I believe we have already studied, because there are a number of lectures already delivered, and you have interacted with your previous faculty members. So remote sensing is essentially, it is the science of sensing earth and planetary objects. Nowadays we are also working on different planets and different planetary objects. Okay, and from a remote distance. But what is important, that using the electromagnetic radiation from the objects, which is coming back from the objects, the electromagnetic radiation. So how we can identify the object and how we can characterize the object from a remote distance, that is entire the science is known as the remote sensing. Now you see there are many applications here in geosciences or geological studies. So first 3 basic applications are the geomorphology, or shape of the earth's surface, then lithology, or what are the different types of rocks, and geological structures of the earth crust. Now, what are basically the core applications, or what is the major important applications or derived applications? These are very, very important. You see here, mineral exploration, hydrocarbon exploration, means this is oil and gas, this coal, that comes under these hydrocarbons. Then groundwater, this groundwater prospecting or groundwater targeting, and the groundwater this flow modeling, and the different kind of these applications related to groundwater quality. Then comes this construction material, like your limestone, then marble, like your granites. Okay, there are different kind of materials, stones. Okay, and then comes the engineering geological investigations, environmental impact assessment, geological hazards like landslide, like earthquake, okay, like volcano, different kind of mining hazards as well. So these are the geological hazards. So see the basic understanding from remote sensing to begin with. What are the different rock types in the earth surface where there are rocks are exposed? That is the earth crust. Okay, and there are some areas that are made of alluvium. That is the loose unconsolidated material. Now wherever there are rocks can be broadly of 3 types. You know that. First is the igneous rocks. These are They formed due to this crystallization from the melt, the magma. Then the sedimentary rocks. This is the rocks. These are formed after by the different processes, different agents like this your rivers, like this your aeolian processes, like winds, like glaciers, isn't it? So different processes they degrade these rocks, broken into pieces, chemically degrade it, then they transport it and deposit in a basin. And after this material deposited, then over the time period, what happens? They are getting compacted. There are some processes happens inside the diagenetic processes, it is known as, and after that they are lithified into rocks. Okay, and the another kind of rocks is the metamorphic rocks. These are formed due to metamorphism, means due to this your increase in pressure and temperature. So here both sedimentary rocks and igneous rocks can be metamorphosed, okay, due to the changes in the pressure and temperature. Now you see what are the characteristics of these rocks, so that from these remote sensing images we can interpret that this particular area is made of igneous rock, this particular area is made of sedimentary rock, and the other area where there are sedimentary rocks are there, how we can interpret and identify from the remote sensing image. Now this is the illustration what I have put it on the right side. It's a very ideal example. Why? Because in this particular area, all three types of rocks exist: sedimentary rocks, igneous rocks, and metamorphic rocks. Now you see the central part, okay, it is made of igneous rocks here up to this, and the upper part it is the sedimentary rocks, and this lower, particularly this corner, it is made of metamorphic rock. How we can tell that? See, these are the characteristics of igneous rocks. They are homogeneous, they are massive, they are hard, compact, and resistant. Why? Because they are crystallized from melt. They lack bedding, and their texture is very coarse. Okay, so because of that, this your appearance of the igneous rocks is like this. The texture is very coarse. There is the scooping effect, scooping out effect. Okay, whereas sedimentary rocks, they are very soft. They are deposited. They are bedded, layered rocks. They are easily erosible. Okay, and they are very much vulnerable to dissections. So there are a lot of drainage. You can see the surface will be smooth. Their texture is very fine texture, and they have differential resistance to weathering and erosion at the different layers. Some layers may be very hard, like sandstone, for example. Okay, or maybe your some kind of your carbonate rocks. Okay, so and some rocks are very soft, like shale, like clay kind of rocks. So depending on these type of the rocks, there are certain rocks are a little hard and other rock layers are soft. So you get this kind of ridge valley topography. You can find that layered ridge, then valley, then ridge. And metamorphic rock, what happens? Due to the pressure and temperature, pressure has certain directions, no? A direction this stress is applied. So there are some weak planes developed in a particular alignment. Okay, these are the regional foliation planes. Okay, so these regional weak planes, they are very, very vulnerable for this weathering and erosion. Okay, so along these weak planes, this weathering erosion will be more. So that will give you this kind of striations like features. So you'll find on the image some striated appearance. In addition to that, because of this application of this stress, there are some structures also developed, like folds, like faults, like joints, fractures. Okay, so from that also you can interpret. Just for example, in the next page, you can see different kind of rocks. Okay. So you see in the upper two samples, they are igneous rocks, and these lower two rocks, they are the sedimentary rocks. You can see there are the layered appearance, they are soft, there is ridge valley topography, isn't it? There are a lot of drainage lines are there, so these are sedimentary rocks. You see here there are the weak planes that gives you these striations, isn't it? So foliation planes and the joint planes you can find here. Basically, this is a granite gneissic rocks. Okay, and here in the lower one, you see in addition to these regional foliations, there are this folded structure. So from this folded structure, you can also interpret that this has underwent some kind of stress, which was responsible for the development of this folded structure. Now coming to the next slide, that is all about the geological structures, as we have been discussing in the previous slide about the folds. So what are the geological structures? Geological structures are the deformational structures due to your application of the stress or due to the tectonics that is related to this movement of the these plates. Okay, the major geological structures like folds, faults, and fractures or joints as well as unconformities. Now you see remote sensing why so important for this geological structural feature identification is that here you can have a synoptic view of these geological structures. For example, if it is a fold, okay, you can see the fold in totality. But if you go to the field, go to the ground, if you go to a particular place, you can see only that part, isn't it? If you visit here, you can see this part only, but you won't be able to know what is happening to this part. Now, depending on this attitude of this folded bed, you can interpret something that fold is dipping towards this. The strike is like this, but you won't be able to interpret the geometry of the fold. But if we have a remote sensing image, then from this image we can interpret broadly. Now, selective ground truthing, if we do, then we can calibrate it. Okay, and this we can have a much more refined information, much more refined understanding about the geometry of the fold. In some cases, the fold may not be exposed to the surface. Sometimes it is buried underneath, maybe very near to the surface or a little deeper. So in such cases, what happens? It may give you some topographic high, or there may be some kind of anomalies. That anomalies will be reflected to the drainage. Okay. So from these topographic and drainage anomalies, you can also interpret that there is a folded structure. I'm not going to these, what are the different kind of anomalies, but essentially there may be topographic high when there is a anticlinal fold, or topographic low when there is a synclinal helix. Okay. Now there are other geological structures like faults and the lineaments. Lineaments consist of fractures and joints. Like here you see this particular line where we have shown by two arrows. Okay, this is displaced like this. Okay, this is the Shivalik rocks. In fact, this is the river is known as the Yamuna River, and this is the Yamuna Tier fault, or basically it is a strike slip fault. So this is the Yamuna Tier fault. Tier fault is where this your thrust sheet is getting strike faulted. Okay, so now you see this is the Shivalik here, and this is Shivalik here, and it got shifted by this Yamuna, this your strike slip fault. Along this fault only, this Yamuna River has flown. Okay. Now there are these weak planes like these fractures and joints where there is no displacement, but their weak planes exist for a long distance. Okay. So in such cases, we can have some tonal anomaly or some topographic breaks. So from this linear topographic depression, we can interpret that there is some your fractures or joints, or there may be some vegetation alignment along a particular lines. Okay, or there may be soil infilling, or this soil moisture may be high along some particular lines. So those lines represent that they are the fractures or joints. Sometimes drainage will flow along these weak planes. Okay, so drainage segment anomalies are indicative of these your lineaments. Now going to the next this your application, that is the geomorphology. That is what is the shape of the earth. Okay, it deals with the physical processes and the materials involved in shaping the earth's surface as a function of topographic elevations. Okay, that is the height or altitude of the topographic surface, and what is the slope and how the slope is changing. This shape of the slope or the rate of change of slope, that is the surface ruggedness. Now in geomorphology, the basic unit of geomorphology is a landform. And you know this landform is a multivariate feature. Okay, it is a function of lithology, structure, geomorphic processes, climate, and time. Okay, and how remote sensing is important for geomorphology or for the identification of the landforms, because remote sensing provides you the synoptic view of this landform. That is one thing. The entire landform you can see in totality, and from the remote sensing based this topographic elevation information also, this landform can be interpreted. Okay, So remote sensing provides you the synoptic view of the landform and elevation related information. Okay, so in geomorphology we study many things, so we'll not discuss here in this particular session. There is the morphography, that means how they look. Okay, what is the measurements, what is the this your dimension of these landforms, what is the shape. Okay, and then how they have been originated, that is the morphogenesis, and how these different landforms have originated at different times, that is the chronological ordering of these landforms, and morphodynamics, what is the present day these geomorphic processes. Now see, for example, this is the fluvial landforms in this particular area, and here there is the this your mountain this area, isn't it? So it is the hills and valleys basically. Okay, in the mountainous region, what are the landforms you can see? You can see the ridge and the valleys. So ridge and valley, this topography you can see here. Okay, but what is most important in the fluvial region, you see, you can see one meandered river. You can see many other features or landforms. For example, you can see the horseshoe kind of magnets, isn't it? What are they? Horseshoe lakes. Then you can see the this your natural levees, that is the at the bank of this active floodplain. But at the same time, you can see the paleo natural levees that previously it was the at the river bank, but nowadays this active floodplain is not flowing there. It has migrated to other places. So present day, this natural levee exists here, but the previous natural levee was somewhere here. Then you can also interpret there are the alluvial plain. So this is the alluvial plain, this is the active floodplain. There you can find, for example, here this is the sandbars, isn't it? So there are many landforms you can interpret from remote sensing image. Okay. Now coming to this your thermal remote sensing. Thermal remote sensing, you can understand from the terminology itself, it is related to the temperature of the Earth's surface, and because of the temperature of the Earth materials or planetary materials, what kind of thermal radiation it emits. So that can be sensed from this your airborne or this spaceborne platforms. Okay, so from airborne sensors or spaceborne sensors, you can receive this thermal radiation, and from this thermal radiation you can retrieve the temperature and a number of thermal parameters like your thermal conductivity, then diffusivity, then thermal inertia. Okay, so those kind of these thermal parameters you can obtain, and from that you can interpret. Now you see in the thermal remote sensing, 3 micrometer to 35 micrometer, this is the region, is popularly known as the thermal infrared region, particularly in case of terrestrial remote sensing. Okay. Now out of this, see there are the atmosphere in between the satellite and the Earth's surface. So the entire this region is not transparent. So the region between 8 to 14 micrometer, basically here you can see white means it is the transmittance is high. That means it is radiation from the Earth's surface, it can go through the atmosphere and it can reach to the sensor. So this white high means transmittance is high, so it can go through the atmosphere. And where it is entirely black means it is completely opaque, means the atmosphere, through this atmosphere, your radiation cannot pass through. Okay, so it completely absorbs atmosphere. Basically, atmosphere completely absorbs this thermal radiation. It does not allow to pass through this atmosphere because of certain atmospheric gases like H2O, water vapor, then carbon dioxide. Okay, sometimes oxygen as well. But you see, in this 8 to 14 micrometer range, there is a 9 to 10. There is ozone layer. Okay, and the ozone layer that absorbs thermal radiation. So 9 to 10. So that is why in spaceborne thermal sensing, we can have this range from 8 to 9, again from 10 to 14 micrometer. In between 9 to 10, there is the ozone absorption band. But there are two other your bands are there, atmospheric windows are there, that is 3 to 5 micrometer. Another is around 17 to 25 micrometer. But you can see here that here transmittance is much lower than 8 to 14, and in this case even very low. isn't it? 1725, 17 to 25. So what we see that from airborne platforms, we can use both 3 to 5 and 8 to 14 micrometer, whereas from spaceborne these platforms, we use essentially this range, but not this full range always, but 10 to 12 micrometer we use always, but sometimes we use 8 to 14 also, but we exclude this 9 to 10 micrometer. So this is the range where thermal remote sensing works, particularly for the earth sensing or terrestrial remote sensing. And the 1725 is not very much used because here the atmospheric window, it is quite subdued, and here only low temperature objects have substantial radiation in this particular region. Okay, so terrestrial sensing means this ambient temperature is around 25 degrees Celsius. So at that particular temperature, the maximum radiation takes place in 10 micrometer. So that is why this particular window is very, very important for terrestrial remote sensing, but it is not. Okay, and this is important for the higher temperature targets. Like for example, if there are some volcano, then coal fire, or even forest fire, although it is not a geological phenomena. So in such cases, 3 to 5 micrometer is much more useful than 8 to 14 micrometer. Now you see why thermal remote sensing is very, very important. Although it is less used in many cases, we are not using it much because of the non-availability of the data at this required spatial and temporal resolutions. So data is not available at our desired level of spatial and temporal resolutions. But you see this in case of your rocks, what is the major composition is the silicates. In case of silicates or in case of carbonates, these absorption peaks of the rocks essentially exist in this thermal remote sensing region, thermal region. Okay, not in the region is 0.423 micrometer, which is known as the optical region. Not there. In 0.423 micrometer, in such cases, you will find many oxides like ferric oxide, ferrous oxide. Okay, so sulfate, so many minerals like this. But silicates are essentially giving this characteristic absorption peaks in the thermal region. For example, you see in case of your granites, diorites, gabbros, olivine periodites, that is starting from the acidic rocks, then your intermediate rocks, then it is a basic rocks and ultra basic rocks. You see the absorption peak shifts from 8.6 micrometer, where the silica rich rocks, where the free silica or quartz minerals are available, is corresponding to aster band 11 for granite. And in case of ultra basic, it goes to 10.7 micrometer, the same absorption peak. See, in one case where it is silica rich, 8.7, and where it is silica deficient, it is 10.7, 8.6 and 10.7. So this is your absorption peak locations. Okay, from that you can identify what kind of rocks broadly it is. Okay, and this band is known as the Ristretto band. Similarly, for a different kind of your silicates, they have the characteristic absorption peaks which can be used to identify that particular rock. It is also true for the carbonates, and particularly for hydrocarbons also, they have the characteristic absorption peak in the thermal region. Then that means in case of oil, petroleum, or in case of coal. Now you see, in case of multispectral thermal sensing, okay, because the thermal sensitivity is not same for different bands. Because higher temperature objects, maximum radiation takes place in the shorter wavelength, and lower temperature objects, maximum radiation takes place in the relatively longer wavelength. So if you use multiple bands, okay, so where the wavelength is shorter, here the higher temperature objects will have more radiation, and where the temperature is lower, okay, for such objects, in longer wavelength, the radiation will be more. So now we generate one false color composite image by using 3 bands. Okay, you find that different geomorphic landforms, like your alluvial fans, like your piedmonts, or these in and around the floodplains, or it is these hills and valleys, that is the compact rocks exist. They have different colors, isn't it? Why they have different colors? Because their sensitivity to temperature sensitivity is different. Their thermal inertia is different. So in different bands, they radiate differentially. And because of that, you are getting different color. Some cases, red is more dominant. So that means red band radiation is more. And some cases, blue is dominant. So blue band radiation is more. In fact, these are the different thermal bands only. Similarly, in case of these lithology, particularly in case of volcano mapping, where the different lava flows exist at different times. Okay, so eruption takes place at different times. So they have different stages of cooling. Their temperature is different. There are different this level of gassiness, different stages of this your soil development, or sometimes vegetation growth as well. Okay, depending on that, their temperature is different, thermal inertia is different, and so thermal radiation is different. And because of that, in case of multispectral thermal sensing, you have different colors, which can be very much useful for interpreting these volcanic layers of different age. Okay, and different cooling conditions. Now see, similarly, optical and thermal, there is another part of this electromagnetic spectrum is the microwave region. Microwave region, essentially from 1 millimeter to 1 meter, this is the microwave region. But in case of radio ranging, which is known as the radar, remote sensing, in such cases, we use essentially the centimeter wavelength. Okay, and when it is a synthetic aperture radar, that means the antenna is synthetically produced, okay, by this your data processing using this Doppler principle, for example. Okay, so this synthetic aperture radar your data. So in such cases, we use only the centimeter wavelength starting from around X band, that is 3 centimeter is the central wavelength, to about the P band, where the central wavelength is around 60 to 70 centimeter. Now, what is important in case of radar remote sensing for geological studies is something like this, because you know radar does not look down. They are not nadir looking, but they are up nadir and side looking. So because of that, they are sensitive to surface geometry. Okay, so they're sensitive to surface geometry that provide information on geomorphology and geological structures. So geological structures, they are highlighted through the topographic elevation differences. Okay, so because of that, this geological structure as well as geomorphology itself, it is a representation of the topographic elevation, slope, and the rate of change of slope or the slope shape. So that is why this, in case of radar image, because it is very sensitive to surface geometry, geomorphology and geological structures are getting much more highlighted. You can see down below how much it is highlighted. This is the Himalayan region and this is the Sivalik. Okay, this is basically in and around Dehradun we are talking about. This is Dehradun city. This is a residual hill, Rasiwala hill. Okay, so you see here the microtopography is so much prominent. Like here you see the Shillong plateau. So plateau is so clear. This is the plateau fringe area. Okay, and this is the plateau top, and this is the mining area. This is the Jharia coalfield. Now you see its sensitivity to surface roughness. That is also very, very important, because particularly in case of vegetated terrain, it provides information about the lithology, or it gives you some information about this your land surface ruggedness. Like in particular example, you see this open cast mining area is very rugged. So that is the reason it is giving you a lot of the back scattering. It is, we do not call it radiation, but it is scattering back. So that is the reason it looks white, isn't it? Now you see there is this radar image, it is also very sensitive to the moisture content or dielectric property of the material. That is the reason there are unconsolidated material like alluvium, like soils. In case of geology, altered rocks, like in case of these mineral deposits like gosans, isn't it? So they are made of hydrated minerals. Okay, so those kind of material, there the H2 content is high, so dielectric property is high. So in such cases, it gives you bright appearance. Okay, and the fourth one, its capability to penetrate through vegetation and ground. So radar waves, you see here the wavelength is very long, centimeters. Like it may be the 5 centimeter, it may be 10 centimeter, it may be 25 centimeter, or even 60 to 70 centimeter long wavelength. So because of its long wavelength, it can penetrate through vegetation and it can penetrate through ground also. So you can have in a forested area, you can have information about the terrain. That is what are this surface, rock surface looks like. The vegetation is there in a forested area, but you can have information about the rock surface terrain. Similarly, you can get information about the subsurface geological features like your buried channels, like active faults in an alluvial terrain. So those kind of features you can identify using this radar image because it penetrates through material, but it penetrates only few meters, not kilometers or hundreds of meters, only few meters it penetrates. Also, it can also highlight sometimes underground civil structures like water pipelines or oil pipelines, sewerage lines. Also, it can identify in a city, urban environment. Now, see, this just I am giving you one example. This is an optical image from a multispectral image. We have converted to a brightness image, a black and white image. Now, if we compare this black and white image from a multispectral optical image with the microwave SAR image, a medium resolution NVSat SR is very old image, and a radar SAR image, it is relatively higher resolution. Resolution is around 5 meters or so. In this case, it is around 20 meters, 25 meters. Okay, and this is also around 30 meters resolution. Okay. Now you see, in this case, even if it is the resolution is comparable, see this topography, micro topography is very much highlighted here. But there is a problem also. There is the geometric distortion of your mountainous terrain. That is the Himalayan region. There are a lot of your geometric distortion happens about the surface. So on the image, it gets distorted. This is difficult to interpret sometimes. And in the higher resolution, that is the radarsat fine beam image, you can see here your geomorphological details is much more highlighted, isn't it? Similarly, in this case also, you can see the dissections. There are these channels are so much clearly you can interpret. Now, this another example in this radar remote sensing is your rock type, particularly using the surface roughness. Where the surface is rough, there will be more energy will come back, the more backscattering will happen. So those areas will look bright, and the other areas will look relatively dark. You see, this is very dark area that is essentially made of shale or clay type of rocks. Those are very fine grained rocks. Okay, and this intermediate one, that the sandstone, you see here the sandstone is relatively the grain size is coarser than the shell, isn't it? In case of sand size grains, the 2 millimeter to 1 by 16 millimeter, whereas the shell is less than 1 by 16 millimeter is the diameter. Okay, and clay it is 1 by 256 and less. That is the millimeter in diameter. And in case of limestone, you get very coarse your texture. It's not the grains, but the surface is very, very rough because it is hard and compact. So because limestone is very rough surface, so it appears bright. Sandstone, it is less rough, but more rough than the shale or clay. So it looks also bright, but not as bright as limestone, whereas the shale and clay appears darker shade. Okay. Now you see, because the radar image, it highlights the surface, this roughness property and the surface geometry. So if you can merge this radar image with this multispectral optical image, then you see there are this much more miracle happens. So the features can be much more highlighted, isn't it? Like here, if you could have only the optical multispectral image, then many of the features you would lose, you would miss. Okay. For example, here your buried channels or subsurface channels, it can be interpreted very nicely because radar image has been merged with the optical multispectral image. Similarly, you see these geomorphological these features. Okay, these structural hills. Okay, here the microtopographic information is much more highlighted. Similarly, you see in this area the dunes, these longitudinal dunes. Okay, so the aeolian landforms are very, very clear because the radar image is fused with the optical multispectral image. Also, you see there is an impact crater and the crater boundary is so sharp. and because the radar image has been merged. Okay, so many such features will be highlighted while you will be used a huge product. So merged product of the optical multispectral image and the radar image. Now see, in this case here, in case of radar image, you can use different polarizations also, like horizontal, horizontal, vertical, vertical, horizontal, vertical, vertical, horizontal. That is for a linear polarization. Then there comes circular polarization and many more. So I'm not going to that. Just for example, if you use very simple kind of linear polarization, this HH and HB. One is this like polarization, HH and HB. You see, in case of HH, you are getting the surface features are very much highlighted due to the high surface scattering. And in this case, volume scattering is much more highlighted. So you are getting the subsurface features are more highlighted. See, the same area, you see, subsurface features is a fault is very much clear here, which is not very clear in this case. And in optical image, absolutely not seen. Whereas in case of HB polarized radar image, there is a subsurface fault can be highlighted and it can be mapped. Now coming to the different applications. To begin with, for example, the groundwater studies. You can do this groundwater targeting, means where the groundwater availability is more. Okay, then where groundwater recharge can be estimated and how this recharge can be, which area the groundwater recharge can be done efficiently. That identification of the recharge site, it can be done from remote sensing data. And there are other things where GIS plays very important role. That's numerical, the flow modeling and quality assessment. For example, here in Rajiv Gandhi National Drinking Water Mission, that particular project conducted by ISRO, at different stages. Okay, here we have this groundwater prospect map for the entire country. This is just an example where we have carried out this groundwater prospect mapping of the National Capital Region. So this is 1:20 50,000 scale, and we are working on 1:25,000 scale. You can even go down to larger scale your groundwater prospecting. Then comes this groundwater prospecting and quality. So you can combine these two together. And here we have prepared this kind of map, groundwater prospect and groundwater quality for the Delhi region. Now, in case of Dehradun region, how the groundwater flow is happening. Okay, so that also we can do by some vectorization of the groundwater flow. We can do that. This is the groundwater flows are happening underneath. Now see here, simply from a satellite image, we can interpret a lot about the groundwater availability, whether groundwater availability is good or bad, and whether the groundwater available near the surface or much deeper the surface. Those kind of information you can, the first-hand kind of information you can interpret from a satellite image. Here, for example, using these three basic criteria, that this at the surface, whether the soil moisture is high or low, the vegetation density is high or low, whether there are the influence streams or effluent streams are occurring. Based on that, in this is Shivaliks and this is the Piedmont alluvial region. So in this Piedmont alluvial region, we can interpret which area groundwater prospect is high and groundwater available shallower to the surface, and which area groundwater prospect is low and groundwater available is deeper. For example, this is the Bhabar zone. You see here soil moisture is low. That is why the area looks bright, white. Okay. Vegetation density is low because it is standard FCC, and redness is low means that means here vegetation is less. Okay. And you see also river beds looks dry. There is no water. Whereas if you go down to the Tarai region, and that means the Piedmont alluvial to alluvial region, then what happens? You see redness increases, so vegetation density increases, soil moisture increases, blueness increases. Okay, soil moisture means blueness in standard FCC, and you see suddenly this river gets water from where? So here what happens? There the streams, the base flow coming to the surface. So where in such cases in this area, what happens? Whatever this rainfall or surface water was there, it is percolates deep inside, and then it is flowing as the base flow, and the base flow is appearing to the surface here. So that means in this area, groundwater availability is high. It is very near to the surface. Okay. So this kind of interpretation you can do here, whereas in such cases, groundwater availability is low and it is available and much deeper. Got it? No? Now, simply remote sensing is not enough. We need to do some geophysical investigation. In fact, remote sensing and geophysical investigation we need to do together. Okay. First, we interpret from remote sensing data, and broadly we identify this is the high prospect zones. Now, in such high prospect zones, we do this geophysical investigation, essentially resistivity survey. Okay, and resistivity survey can be vertical electrical sounding we can do, or we can do electrical resistivity tomography or ERT. So we see here in case of ERT, you can see this particular area is a low resistivity zone. So here basically the water occurs. This is the aquifer. Okay, so huge thick aquifer occurs here. While we are drilling, we find there are a lot of water is flowing out. Okay. Now, see, there are from spaceborne gravity. Okay, that is the GRACE, the name of the mission, GRACE and GRACE, this FO. Okay, from that we can have a regional scale the groundwater storage information, and that the first time it came into this reality, we came to know that from these studies of the Rodel, that in the northwestern part of India, there are the groundwater storage change is depleting at a very rapid rate. So groundwater depletion is very high, and that was shown here. That groundwater depletion on an average there is the 4 centimeter per year. But after that, there are some advancement happens in the data processing and then forward modeling. Okay, so Chen et al. They have shown this area is similar only, but a little bit there are this your geographical this your changes are there. But what is important here, this what the estimate they got it is around 8 centimeter per year. It is much more, and you know this is the maximum groundwater depletion happening worldwide. It's very high rate of depletion. But we studied in the early 2010s or so. So, and we have carried out some advanced processing by downscaling with the in situ data. And you see, this is the information about the groundwater storage change. And what we got exactly, you see this kind of depletion we have found around 11 centimeter depletion we found in this area. In some area, there are recharge also taking place. And some areas recharge is even up to 12 centimeter, particularly during the monsoon. This is information about the monsoon. Now, if you use the groundwater level change, that is continuously this monitored by Central Groundwater Board. They are collecting this groundwater level data. Okay, and 4 times a day, 4 times a year. So like your November, then February, then your May, and then this August. The 4 times they collect the groundwater level data all over the country, most of the places. In some cases, they are collecting even monthly. Now, using this groundwater level data, we have calculated the groundwater storage change, and this is the information you can see. Okay. So there are broad matching, but it gives you more in situ information. But at the same time, Central Groundwater Board, these wells from where they collect this groundwater level data, they are mostly shallow groundwater levels. They have some deeper levels also, but this number of deeper groundwater, this well data are much less. Okay, so they do not give the complete information about the aquifer or groundwater storage change. Now, come to other applications like mineral exploration. Here, mineral exploration, there are the many applications you can have. For example, the first and very important application is the surface mineral identification. So mineral deposits, those are at the surface, occurring at the surface. Surface mineral deposits can be explored efficiently by these remote sensing techniques because they have the characteristic absorption peaks. So from this absorption peak, you can identify that particular mineral exists and this mineral deposit can be mapped. Similarly, if the mineral deposits occurring at the deep, then some kind of predictive modeling using different factors like geological structures, like geomorphology. Okay, so different like geophysical information, like what is the gravity, what is the thermal information. Okay, so all those things, depending on that particular mineral deposit characteristics, we can integrate, and we can do some predictive modeling, and we can identify these characteristics of the mineral deposits, at what depth it occurs, and how much mineral deposit you can tentatively you can estimate. Similarly, mineral resource information system, by using the GIS platform we have developed. So this is a prototype. So here all about the different mineral deposits, their reserve, how much reserve is available, what is the grade. Okay, so all those information you can your store in a your GIS platform. Okay, and this is known as the mineral resources information system. So this kind of information system we can have. Now you see, in case of mineral identification or mineral exploration, you can see that different spectral bands are important for identification of different mineral deposits. For example, this 0.4 to 0.7 and 0.7 to 1.5 micrometer, that is basically this is the 0.4 to 0.7 is the visible region, and 0.7 to 1.5 is the near infrared region, isn't it? So in this region, you see there the ferric and ferrous iron oxides, okay, manganese, copper, nickel. So these mineral deposits have characteristic absorption peaks. Whereas in case of shortwave infrared region, there's 1.5 to 1.8, that is SWIR 1, shortwave infrared red 1, and 2 to 2.4 micrometer, this SWIR 2, to the hydroxyl, okay, then carbonates. So these mineral deposits, hydroxyl means mostly clay minerals, and carbonates can be identified in this particular absorption, these spectral regions from their absorption peaks. Now, in case of thermal infrared, 3 to 5 and 8 to 14 micrometers, silicates and carbonates, they have the characteristic absorption peaks, so you can identify them. Now, you see, in case of these, your standard, these multispectral bands, this band width are large. So you miss this narrow spectral absorption peaks. So that is why this hyperspectral remote sensing, which gives you very narrow bands, around 10, this your nanometer, 10 to 15 nanometer is the bands after sampling. Okay, and this spectra is continuous. In this case, these are your discrete bands, number of discrete bands, and very large, this wide bandwidth. And in this case, there the very narrow absorption, these your bands, 10 to 15 nanometer is the bandwidth, and it is a continuous spectral information you have. From that, you can identify these mineral deposits. Those are exposed to the surface. Okay. Now, for mineral exploration, the micro remote sensing helps a lot, particularly in case of these hydrothermal mineral deposits. Hydrothermal mineral deposit, you know, here the geological structures are very, very important, because they are essentially, there are the vein deposits or lode deposits. So they are is concentrated at the junction of the fractures and in the shear zones, isn't it? So if you have information about the geological structures like this, your fractures or joints or intersection of the fractures and joints, or the shear zone, like here available the shear zone, intersection of the fractures and joints, you can find in many places. So these are the potential locations of these hydrothermal mineral deposits. Now, if you can merge this multispectral optical this your image with this radar image, so you have the spectral information of the these your surface minerals. Those could be indicative of these mineral deposits and these geological structures. So from the spectral information and the structural information, we can have much better this control about the identification of the mineral this deposit or mineral exploration. Okay. Now see, in case of hydrocarbon exploration, so we have given an example about the oil and gas only. So here the first-hand information comes from the geomorphic anomaly or the drainage anomaly. Like in this case, you see this is very close to Silchar in northeast India, in Assam. See here the Barak River shows you very anomalous, okay, circular anomalous anomaly pattern, isn't it? Barak River, you see, is a very circular pattern, isn't it? So this is anomalous pattern. Why it happens? Why the river cannot flow here directly like this, but it is going a roundabout way, and it makes a circular this pattern. Why? Because there is some subsurface high. There is a folds underneath. Subsurface folds occurs, and this subsurface folds basically it is a structural trap where oil got accumulated. Now, if you go for this your geophysical survey, like your seismic survey, here you see the seismic profile. It gives you very clearly what is the geometry of this your petroleum trap. Not only that, number of faults also you can map here. Okay, number of faults, and it is the upper surface of this your production horizons. That is the trap horizon of the structural trap. Now see, this is how it has been interpreted by this your ONGC. Okay, KDMIP is a part of this ONGC, and now you see here from the this satellite-based this gravity. That is what I have already explained to you. The space-bound gravity like grace. Okay, kind of information also regionally you can interpret the regional oil fields if it exists at some places. So regional oil field will give you the low gravity zone. That is what you can see, a low gravity in this particular area you can see here, isn't it? So this low gravity zone, so that tells you that there is the extensive field of this oil field exist subsurface. Okay. So this is very near to the Silchar only. So here it gives you very low gravity zone. Now coming to the geological hazards, for example, to begin with, a landslide is one of the most important geological hazard in India, particularly in the mountainous terrain of the Himalaya and the Western Ghats. Now here you see if it is an active landslide, then landslide scar identification can be done very easily, either by visual interpretation or by image segmentation or multi-table change detection. Similarly, old or dormant landslide can be interpreted. There are some interpretation criteria we have, and potential landslides also we can interpret using this. What are the causative factors like the topographic slope, like what are the rock types, what is the geomorphology, what is the drainage, okay, what is the how the seepage is taking place or weak zones. All those things, all kind of causative factors, if we integrate, then we can assess what is the susceptibility zone for landslide. Then if you use some kind of advanced techniques, you can also identify where if there is slow movement is taking place or not. That we'll explain in the next slide. Now you see, in case of this landslide, but in case of terrestrial photography, you can map, you can identify that in the satellite image how it looks like, isn't it? Like a spoon, isn't it? Like a spoon geometry. So that tells you that it is a rotational landslide. It is coming like this, okay, scooping out the mass, and then it is falling down in Uttarakhand, Kandi area. Now this landslide hazard assessment or susceptibility mapping we do using different layers like your rock types, then your geomorphology, okay, and you see it is before the landslide how it looks, and it is after the landslide. It is the panchromatic image before landslide and after landslide. So you can map this landslide scar very easily by this image segmentation or visual interpretation techniques. Now, this landslide hazard zonation, after integrating all, we can interpret that high hazard zone is here, exists here. That similar studies we did even before this Uttarkashi landslide occurred, and we identified this is the area where the very high hazard zone where landslide can take place anytime, and it occurred in 2000. Only 2000 this map was prepared, and 2001 this Boronavat landslide occurred. This is the landslide. Again, this landslide occurred later as well. So we did this mapping and hazard zonation in the larger scale up to 1:10,000 scale using airborne data. Okay, nowadays we can have satellite-based data with a very high resolution data is available, isn't it? PlanetScope gives you very high resolution, or ISRO also gives you your spatial resolution even up to the this your 0.4 meter, 40 centimeter or so, 37, 40 centimeters, something like this. So even less than a meter is the size of the pixel. That kind of satellite images we provide from ISRO. See, similar hazard zonation was done for the northeastern region from Shillong to Aizawl, and you see this is the how this your this in Mizoram area, how this ridge valley topography you can see here of the sandstone shale like this. Now you see, as I was discussing, so one is susceptibility, vulnerability, or risk assessment. Another is what is the predictability of the landslide or slow movements. If there is any slow movement is happening before the major the sliding phenomena, that can be mapped by this advanced technique like interferometric SAR technique. Here, one study was done, a pioneering study in the 1990s. See, due to this landslide, the movements can be mapped. And here, each color cycle represents this lambda by 2 of the this your radar band. Your radar band wavelength was 5.6 centimeter C band data. So each color cycle represents 2.8 centimeter movement of the terrain. Okay, due to this landslide. Maybe before the landslide, the slow movement is very, very useful for predicting when this major movement can take place. Okay, similarly, this is another area that is in the Canada. Okay, the slow movement was identified here. Okay, based on that, you can have some predictability analysis. Now, for much more defined this information, so or landslide prediction, you need to know where is the slip surface. And for getting the slip surface, that means this is the interface between the this your loose unconstituted material and this is the hard rock surface. Okay, the slip surface where the landslide mass is sliding down. Okay, so for getting that, you need to conduct a geophysical survey. So geophysical survey and geotechnical this your analysis, geotechnical analysis gives you the what is the rock mass strength. Okay, what is the this your shear strength and what is the cohesive force. Okay, so those kind of information you can get. So now, if you have all those information with you, then this landslide predictability becomes much more easier. Now coming to these earthquake studies. So just few years back, there was the Nepal earthquake. So the major earthquake happened, no, 7.8 magnitude earthquake occurred. And you know, there are many casualty happened, okay, around 10,000, 9,000 plus. So first, this major shock has a magnitude of 7.8, and there are many multiple these aftershocks. With one of the major aftershocks has a magnitude of 7.3. Okay, that occurs here in Kodari. This is the main shock, and this is the aftershock. Now, using this difference in SAR technique, we can produce this land surface displacement, this map from this due to this earthquake. Like you see, due to this main shock, what kind of movement has happened? Okay, here in the legend you can see each color cycle represents 25 centimeter. So that gives you something like very close to the Kathmandu city. There was an uplift of around 165 centimeter along the radar line of sight. And on the north, that is in the northern side, this is MCT is somewhere here. So the other side, this here, what you see, there is this subsidence of around 60 centimeter. Okay. And in case of Kodari area, you see here, there are similar kind of movements you can see, but because the magnitude was less, it is only 7.3. So this area, affected area is much less, and the total movement is also much lesser than this. Here you see total uplift near Kathmandu, so it is around 65 centimeter. So on the southern side, and on the northern side, this subsidence is around 35 centimeter along the radar line of sight. This is the situation. From that, you can obtain this. What is the peak ground acceleration? You have to use some other this your information, like what are the geology of this area, like what are the rock types, what is the fault characteristics, what is the distance from this main shock. All those information you need. But from this displacement information, and from that you can interpret what is the probable rupture zone. You can obtain this, what is the likelihood peak ground acceleration at that particular location. And from this peak ground acceleration, what kind of damage could occur, that you can estimate. Okay. Similarly, there are another kind of application is like active tectonics related to the previous slide only. So where do this maximum this your energy will be released during the time of earthquake, where there are the weak planes exist, and active faults are the faults where the activity is happening intermittently. Okay, so identification of active faults is very, very important in the Himalayan region or in the Himalayan foothills. For example, in the Piedmont alluvial region, you can see there are the topographic anomalies and the drainage anomalies are very, very prominent to identify these active faults. Okay, you see the drainage anomalies, and here you can see the topographic break. From that, we can very efficiently and very nicely we can interpret and identify these active faults. Okay, now if you conduct some geophysical survey at that particular locations, like you see here, this is the active fault likelihood location, that what we get from the satellite image interpretation. Now from this your ground penetrating radar survey as well as from resistivity survey, we can very nicely we can identify or we can decipher what is the subsurface geometry of that active fault. That helps us a lot to estimate what could be the likelihood seismic hazard at that particular location. Similarly, there are other kind of geological hazards like your coal fire hazard or mining subsidence hazards. Okay, they are basically anthropogenic hazards in many cases, but some are naturally occurring, like coal fire can occur due to spontaneous combustion, that is a natural fire, but in many cases they are anthropogenically originated. Okay, so now you see in case of Jharia coalfield, which is one of the 54 Gondwana coalfields, this is the Gondwana coalfield region. So there are coal fire is this worst situation in Jharia coalfield. Okay, and not only today, it is started from 1980s or even before. Now you see here the spatiotemporal dynamics of the coal fire we have studied for the Jharia coalfield, and what is the coal fire area, how it is changing with time, starting from 1990s to till date. Here we have given information up to 2013, but we have studied 2020 or so. So we find this kind of situation, how coal fire is changing. Even today, there are a lot of coal fire exist in Jharia coalfield. And because of the coal fire, their voids develop because the fire, it consumes, it burns this subsurface coal or the pillars. After this first phase of mining occurs, there some pillars exist. So pillars, it can burn out, then there will be subsidence can take place. Also due to underground mining or because of the waterlogging of this previously this mined area. Okay, there can be subsidence can take place. So that also we have studied. Like here you see this in case of coal fire mapping, some kind of modeling we did, pixel integrated temperature modeling, and based on that we have done some kind of thresholding also for coal fire detection. And here the surface coal fire and subsurface coal fire we have identified. And this is the transitional zone between background and the fire zone. And here you see a very old photographs in the 1990s, and some photographs are even recent. Okay, so coal fire very near to the Jharia coalfield. But nowadays, so much blazing coal fire is much very, very less. Okay, this is in the previously, particularly in the 1990s, lot of blazing coal fire we used to have. I see, as I was telling you, that in the mining area there are the hazard due to subsidence also is quite common due to this your abandoned underground mines getting waterlogged, or because of the subsurface coal fire, subsidence can take place. And here interferometric SAR technique can help us to identify the subsiding zones. Like we have mapped by different radar bands like C band and L band, we have identified these subsiding zones. And from the ground-based survey technique, what is used to do by the Bharat Coking Coal Limited in Jharia coalfield, okay, but that is in large scale for that particular mine or for that group of mines, which is known as the area. And this is thus these ground-based survey techniques. These your subsiding areas were mapped by the Bharat Coking Coal Limited. We have is your in a digital platform, we have put it together we have geocoded it, we have mosaiced it, and we have prepared a seamless subsiding map out of that using the information from the Bharat Cosmical Limited. And then we have compared with the what is the satellite-based observation gives you and what we get from here. We find there are some newer areas where subsidence identified from the satellite-based technique. Okay, but here because their miners are important, are interested only identify the subsiding areas in and around the mines where they are going to extract coal. Okay, so that is why many of the areas they have not surveyed. So many such areas we have identified that subsidence is happening. And then there are another application that is the planetary your exploration. So planetary surface composition, what is the this mineral composition of the planetary surface, like moon, like Mars, what are the morphology of the planetary surface, okay, what is the relative age of the planetary surface, okay, different kind of application you can do from remote sensing image, like with iron oxide percentage, this TiO2, titanium oxide, and so the ilmenite percentage. And if there is the crater in and around the crater, you can get the composition, and you can also tell whether the crater is a fresh crater, it is an old crater. Okay, so those kind of application we can do. Similarly, using this radar image, we can interpret what is the surface morphology of the crater. Okay, and what is the this probability of this water ice presence in the crater, particularly deep inside the crater, whether the water ice is available or not. That those kind of information also we can get. That in case of Chandrayaan-1, and this is presently you know that Chandrayaan-3 is fully successful, and a soft landing was possible. There's a rover, there's a lander, there is an orbiter. Okay, so from Chandrayaan-2, so all are now in an integrated manner. The people are studying. We are studying that, isn't it? So here from this Chandrayaan-1, we have the miniature data, miniature synthetic aperture radar data. From that, number of this your analysis you can do, circular polarization ratio, degree of polarization, and then polarization decomposition. From that, you can interpret this probability of water ice in this deep inside the crater. So we identified this water ice from this crater, from both from this the radar data as well as from the hyperspectral data. And in Chandrayaan-2, IIRS, this is the name of this sensor, hyperspectral sensor. From that also, this presence of water ice was confirmed. Similar to Chandrayaan-1, there were from M-Cube and from the miniature, this water ice presence was this for the first time it was discovered, and in Chandrayaan-2 it is much more confirmed. Now, if you have some spaceborne radar sounder, you can have subsurface information also. So you can get what are the layering of these your regolith layers in case of moon, or subsurface layers you can interpret. Okay, but in case of this remote sensing, should be studied in conjunction with this your ground-based observation. Okay, so that we can calibrate and validate the satellite-based observation. So that is the reason, like all very reputed remote sensing organizations or centers, Indian Institute of Remote Sensing also hosts many ground instruments. These are some few samples of that, starting from these core station, total station, resistivity meters. Then we have this spectrophotometer, and this is the spectrophotometer in the thermal region known as the FTIR. Then we have a dedicated engineering geological lab. This is the ground penetrating radar. So many more things. The electric resistivity tomography. Okay, so there are a lot of instruments we have. Some are instruments are portable. Some instruments already installed on the field. This is the field laboratory, and some we carry and we take the measurements on the field. And sometimes we have the laboratory in the in-house laboratory at IIRS itself, and we bring the samples and we analyze. So these are important to confirm whatever interpretation we do, to calibrate the information what we derive from the remote sensing images. With that, I conclude and thank you. So